Welcome to the introduction of number systems, a fundamental concept in information technologies. Let's explore the common number systems, decimal, binary, octal, and hexadecimal, and their usage in human and computer contexts. Here, we see how quantities are represented in decimal, binary, octal, and hexadecimal systems from 0 to 7. Continuing, we observe the representation of numbers 8 to 15 across these four number systems. Finally, let's look at how numbers 16 to 23 are depicted in decimal, binary, octal, and hexadecimal systems. Now, let's discuss the possibilities of converting numbers among decimal, binary, octal, and hexadecimal bases. Here's a quick example showing how the number 25 can be converted into binary, octal, and hexadecimal. For fun, let's see how a number in decimal can be converted to another number in decimal. Understanding the weight of each digit in a number is crucial for conversion. Here, we break down the number 125. Next, let's explore how to convert a binary number into a decimal number. The technique involves multiplying each bit by 2 raised to the power of its position and summing the results. Here's an example of converting the binary number 101,011 to its decimal equivalent. Now, let's look at how to convert an octal number into a decimal number. The technique is similar to binary conversion but uses base 8 instead of base 2. Here's an example of converting the octal number 724 to its decimal equivalent. Next, let's explore converting a hexadecimal number into a decimal number. This technique involves multiplying each digit by 16 raised to the power of its position and summing the results. Here's an example of converting the hexadecimal number ABC to its decimal equivalent. Finally, let's see how to convert a decimal number into a binary number. The technique involves dividing the number by 2 and keeping track of the remainders to form the binary equivalent. Let's start with an example of converting a decimal number to binary. Here, we have 125 in decimal, and we want to convert it to binary. By repeatedly dividing by 2 and recording the remainders, we get the binary equivalent of 1,111,101. Next, let's look at converting octal numbers to binary. Octal, decimal, binary, and hexadecimal are all interrelated, and understanding these conversions is crucial. To convert an octal number to binary, we convert each octal digit to its 3-bit binary equivalent. This method ensures accuracy and simplicity in the conversion process. For instance, let's convert 705 in octal to binary. Each digit is converted to its 3-bit binary form, resulting in the binary number 111,101. Now, let's move on to converting hexadecimal numbers to binary. Just like with octal, understanding the relationship between these number systems is essential. To convert a hexadecimal number to binary, we convert each hexadecimal digit to its 4-bit binary equivalent. This method is straightforward and effective. For example, converting 10AF in hexadecimal to binary involves converting each digit to its 4-bit binary form, resulting in 000100010101111. Next, let's explore converting decimal numbers to octal. This conversion is another fundamental skill in understanding different number systems. To convert a decimal number to octal, we divide the number by 8 and keep track of the remainders. This process continues until the quotient is 0. For instance, converting 1234 in decimal to octal involves dividing by 8 and recording the remainders, resulting in the octal number 2322. Now, let's look at converting decimal numbers to hexadecimal. This conversion is particularly useful in computing and digital electronics. To convert a decimal number to hexadecimal, we divide the number by 16 and keep track of the remainders. This method is similar to the decimal to octal conversion. For example, converting 1234 in decimal to hexadecimal involves dividing by 16 and recording the remainders, resulting in the hexadecimal number 4D2. Next, let's discuss converting binary numbers to octal. This conversion is straightforward and involves grouping bits. To convert a binary number to octal, we group the bits in threes, starting from the right, and then convert each group to its octal equivalent. For instance, converting 101,101,011 in binary to octal involves grouping the bits and converting each group, resulting in the octal number 1327. Now, let's move on to converting binary numbers to hexadecimal. This conversion is similar to binary to octal but involves grouping bits in fours. To convert a binary number to hexadecimal, we group the bits in fours, starting from the right, and then convert each group to its hexadecimal equivalent. For example, converting 1,010,111,011 in binary to hexadecimal involves grouping the bits and converting each group, resulting in the hexadecimal number 2BB. Finally, let's discuss converting octal numbers to hexadecimal. This conversion is a bit more complex but follows a systematic approach. To convert from octal to hexadecimal, we use binary as an intermediary. This method simplifies the conversion process. Let's look at an example. To convert 1076 in octal to hexadecimal, we first convert each digit to its binary equivalent, then group the binary digits into sets of 4, and finally convert these groups to hexadecimal. Now, let's reverse the process and convert from hexadecimal to octal. Again, binary serves as the intermediary step. The technique for converting from hexadecimal to octal also involves using binary as an intermediary. This consistent method ensures accuracy. Here's an example of converting 1F0C in hexadecimal to octal. Convert each hexadecimal digit to binary, then group the binary digits into sets of 3, and convert these groups to octal. Let's practice converting between decimal, binary, octal, and hexadecimal. Try to solve these without using a calculator. Here are the answers to the conversion exercise. Check your work to see how well you did. Understanding common powers of 10 is crucial. Here's a table showing various powers, their prefixes, symbols, and values. In computing, we often use powers of 2. This table shows the values for kilo, mega, and giga in base 2. For example, in the lab, you might see a hard drive's free space displayed in bytes. This can be converted to gigabytes using powers of 2. Now, let's determine the free space on all drives in a machine. Record the values in both bytes and gigabytes. When multiplying powers with the same base, simply add the exponents. This rule simplifies calculations significantly. Binary addition starts with adding two 1-bit values. The results follow a simple pattern. For two n-bit values, add individual bits and propagate carries. Here's an example to illustrate. Let's have some fun with decimal multiplication. Here's a quick example to refresh your memory. Binary multiplication of two 1-bit values follows a straightforward pattern, similar to addition. For binary multiplication of two n-bit values, the process is similar to decimal multiplication. Here's an example. Converting fractions from decimal to decimal can be fun. Here's a simple example to demonstrate. To convert a binary fraction to decimal, multiply each bit by its corresponding power of 2. Here's how it works. Converting a decimal fraction to binary involves multiplying by 2 and recording the integer part. Repeat this process to get the binary equivalent. Let's practice converting between decimal, binary, octal, and hexadecimal again. Remember, no calculators. Here are the answers to the conversion exercise. Compare your results to see how you did. Thank you for your attention.